Then some of the advantages, like if I look at it, because we know like once it becomes, the slope becomes flatter and flatter, the earth pressure reduces actually. So we need less reinforcement. That means compared to a reinforced soil wall, then we can use lower quality of fills, because as I mentioned yesterday, for a reinforced soil wall, we need a good quality granular fill, which is commonly less than 15% fines. But then for the slopes, we can use up to 50% fines. So like for the wall, probably we may have to bring the soil from a large distance, or we may have to use sand. Whereas slope, we can use the locally available soil, which makes it much more cheaper. Then embedment, like yesterday we have seen for the reinforced soil wall, we require some embedment below the ground level. So in the case of slope, it's not mandatory. Like sometimes if it is required, we have to provide, but it's not mandatory. Then wall need a good facing, like blocks, panels like that. But then slope, we can go for a green facing. Like we don't need a like a rigid facing. Then larger tolerance to differential settlement, or even to earthquake, like that. Then face finishing is not that critical. See, when we use a concrete panel or block, we have to get very good line and level. But suppose I have a vegetative facing, then even some undulations, minor bulging here and there, doesn't matter. So that is one of the reasons why we allow poorer quality soil in the slopes. Then this is a very simple exercise. What is the kind of cost savings we are looking at? So I have compared two things. One is a 5-meter high embankment with a 2:1 slope. So I need 10 meters additional land on either side, compared to a reinforced soil slope with the 1:1 slope, like that. So in this case, the extra thing will be the reinforcements. Then I also put a coir geotextile, because steeper slope having vegetation, little more difficult. Anyway, vegetation I need here or here, I will need. Okay, both cases I need. So the additional cost is the geogrids, which I have taken a reasonable price. Then the coir geotextile, the price is given. Then savings, the fill quantity I am saving actually. This. Then land also, either side I am saving. So if I look at 1 kilometer, the saving is kind of this much, like 2.8 crores, which is a large quantity. Like. So, like us earlier, we used to think like, okay, geogrid is some kind of very expensive and exotic material, but that is not so actually. Geogrids is available, like there are at least 4 manufacturers manufacturing here. Then different types of materials actually like available. Availability is good. Price is even 100 rupees. I have taken slightly on the higher side. We can even get lower than that. Whereas soil, it becomes more and more difficult actually. I don't know, in Gujarat, in Kerala, we always say like sand mafia. Like there is no geogrid mafia. Like we have soil mafia, but there is no geogrid mafia. We can easily get it like that. So things are changing. So what is important is like we should think as an option like that. Not that, okay, when nothing else works, you adopt this. Right at the preparation of the planning stage, we have to start considering this technology. Then coming to the components, we have again reinforced fill, retained fill, reinforcement, facing, drainage. Then coming to the facing, if the inclination is less than 45 degrees to horizontal, then facing is not required. Like that. But anything steeper, the spacing is required. Again, we have various options, like which we'll see later also. Then reinforcement again, as we have seen yesterday, like different types of geogrids. We can have woven geotextiles. We can have reinforced non-woven geotextiles. It's possible. Then looking at the fill specifications, like this is the BS 8006. See, actually, BS does not give any specifications to the fill, actually. It actually refers to another, like specification for highway works, which is applicable to UK. They have different. So these are commonly used for walls, but this we can use for slopes, actually. So up to, say, 15 to 45% fines is acceptable. FHWA up to 50% fines is acceptable. But unfortunately, we have a problem. Like, see, we have our MORTH specifications, like which is for road and bridge works. So in this, actually, they have put the same, more or less, the same spec for wall for the slope also. Only thing, okay, 5, I think wall 5 is 30 degrees. Here they have relaxed to 28 degrees actually. So, like it's a, I don't know what are the reasons, I don't know like that. But then it takes the entire advantage out actually like that. So if we need such a good quality fill, then what is the fun in going for a reinforced soil slope like that? So hope, I think probably next revision something will be done. Coming to the design, like again, if you go for a limit state approach like BS, it gives a limit state, external stability, internal, compound. External means failure is outside the reinforced soil. Internal means failure is within. Compound means partly through the reinforcement and partly outside. Then serviceability, like same as for walls, settlement, then post-construction creep strain in the reinforcement. So here we have one more, like because slopes we can use poorer quality soils. So the clay or silt, the soil itself can creep with time. So we have to evaluate that also. Like, then external stability, we can have a bearing failure, forward sliding, slip failure. Again, the importance of this, as the slope becomes flatter and flatter, the the failure mechanisms, the effect reduces actually, like forward sliding. Then internal stability, like rupture of the reinforcement, then bond failure of the reinforcement, same as for walls. Again, compound stability, same. Again, compound also, it can be tensile failure and pull out. Then the flatter slope failure surface is more likely like a circular arc or a logarithmic spiral. Then steep slopes like this two-part, but these are all actually approximations. Like, see, we cannot we cannot force a soil to fail along a circle or a two-part plane. So depending on various reasons, actual failure surface may be vary, but which can be closely approximated by these ideal shapes like that. Then serviceability like settlement, then post-construction strain of the reinforcement, and post-construction creep strain of the saturated fine-grained soils. So when the soil deforms, you'll find the face is slightly bulged. But if it is a green facing with vegetation, it's okay. Like, but in the case of wall, it was concrete block or panel, it would have been a problem. Then like one of the earlier method was there is a method by Jewell, like he considered two-part wedge. Then we can analyze like we can take various trial wedges and analyze the stability. For the wall, it was like a Rankine failure plane, which is 45 minus 5 by 2, that is fixed actually. But slopes can vary depending on the geometry. Then this shows the earth pressure distribution, like the K depends on actually the slope angle. We can determine the reinforcement tensions, like normally once we have this earth pressure coefficient, then we can determine the tension. Like, then basically we have to analyze various trial surfaces. Then the manual calculation is difficult. In the case of a retaining wall, we can also do a hand calculation. It's not difficult. But in the case of slope, because so many trial surfaces have to be analyzed, so solution given in the form of charts. Like before, like computers were became very so popular like that. So here we have the slope angle beta. Then here the angle of shearing resistance, like 50 to 40 degree. This gives the force coefficient, which is similar to a earth pressure coefficient. So we can determine like a particular slope angle and a particular phi value of soil, select the earth pressure coefficient. So from this, we can get the tension in the reinforcement. Then we need the length actually. Here it gives what should be the length at the bottom, what should be the length at the top. So this gives the bottom length. Again, slope angle and phi value of the soil. Here it gives C dash is equal to 0, U is equal to 0, pore pressure is equal to 0, like that. So different conditions, they'll have charts actually. then this gives the length at the top actually. So once that intermediate length, we can interpolate like that, or we can divide it into same length but different, like 2, 3 or 4 heights. So we can do a simple cases, we can do a chart solution. So now, of course, we can go for a program like RESSA or any, most slope stability programs have a provision for reinforcement. So we can analyze any number of wedges. So like here, we can see RESSA. See, RESSA has a two options, like one is translational, which is a two-part wedge type of thing, and also rotational like that. So we can give a search this thing and it will take analyze like that. Then see, in the slope stability analysis, one important thing is, see, how do we know I have located the most critical failure surface? Because we are analyzing many, but then how do we guarantee? Like again, like different programs have different approaches. Sometimes we have what are known as factor safety contours actually. So different centers we draw the contour, and as long as my critical is inside, I know, okay, I have located. In RESSA, they have a known as safety map actually. So here we have these colors, each is a factor safety, like red means 1.17 to 1.3. So all these zones have a factor safety of 1.3. So if I look red zones, then here it is increasing. Suppose I have a critical zone, on either side I have higher factor safety. Then I know, okay, I'm safe. Like look, if I look at here, see this is blue, like that. So it's a higher factor safety. This side also is higher factor safety. So my red zone is somewhere in between. So, okay, I'm sure, okay, I'm confident I have located the most critical failure plane. Then another is the rotational failure, which we use the method of slices. Again, we can choose different methods like Bishop method, Morgenstern Price, Sharma. So many methods are available. The method of slices. So here what is happening, we have a reinforcement layer which develops tension. So that gives, earlier it was only the shearing resistance along this failure surface. That is resisting failure. Now we have one more component, the tension, like that. So that is introduced into the calculation. And here, like if it is a, see normally the geosynthetics are extensible, like, so it deforms. So here we can assume, like here initially it was horizontal, but then it deforms actually, it can even become, there is a kink develops, it can become tangential, like to the failure surface. So that it gives the most effect actually. But we can assume it to be horizontal also, then it is conservative. So RISA allows actually, what do you want? Like you want to take the reinforcement tangential, or do we assume it to be horizontal? Like if you want to be conservative, we can assume it to be horizontal like that. Then again, it gives a search pattern, like we can specify the starting point of the circle and ending point of the circle like that. Then we can like any number of, from here to here, we can specify, then it goes on taking the analysis like that. So here, like this part is important, like suppose it's a complicated geometry, that specifying the search pattern, that is, we have to, sometimes what happens, you give one pattern, you get a particular factor safety. You give a different search pattern, you find again we are getting a lower pay. So we have to little bit spend time on this actually. So this shows the trial slip circles. Then again it shows the safety map concept like that. So here the minimum factor safety is 1.33. So this entire this zone factor safety is between 1.33 to 1.5. This side factor safety is increasing, this side also it's increasing. So I know, okay, my analysis is correct, I have located the most critical failure surface. Then like different complicated geometry we can analyze like that. So this safety map is a very useful concept actually. See now, see one difference actually when we do slope stability. In the case of walls, actually we have taken an earth pressure approach. We know like earth pressure increases as I go down. So intuitively we feel at the bottom I need, tension is more, I need stronger reinforcement. That's the way we design. Like, even in the Jewell's charts also, that same concept, earth pressure, we determine the tension. okay, like we can divide into 3-4 zones, like stronger at the bottom, and but in actually this is actually called local stability, like stability of each layer is analyzed. But when we do with the RISA, like we don't have that concept actually. I can put simply like we put the layers like that, like we don't individual tension on each layer and compared to that strength we don't compare actually. We get the overall like. So when I was using, I had this doubt actually. I was slightly scared also. So because one is intuition tell us okay, like stronger should be at the bottom like that. Okay, when we can put always naturally when we design, I will always put the stronger at the bottom only, but we are not checking each layer like that. So then sometimes I used to do first I used to either pick up from Jewel's chart tension, then put in RISA, then do the stability analysis like that. Then once I discussed with Professor Leshinsky, who made this program, then he said, you don't have to worry about it actually, like that. This pressure approach actually that is obsolete. Nobody does that now. See, if you are doing design it correct, it comes automatically because we are doing both actually, rotational and translational. Because sometimes you find the rotational, it is safe, translation, it's not safe actually. Then first I thought, okay, it is sliding, so I have to increase in the length. Then factor safety doesn't increase. Only if you put a stronger reinforcement, that will increase actually. So what Leshinsky told, like if your analysis is right, both should come more or less same. Your translational failure as well as rotational failure. And in many cases, we get that actually. This actually design I have done. You find more or less it is same actually. Because the failure, okay, we cannot tell the soil, okay, fail this way, that way. Whatever is the worst condition, it will fail. So these are all actually approximations, our bilinear or this, our spiral like that. But sometimes you find it is different actually. Because this translation is only within the reinforced soil zone. Like, but sometimes what happens, this soil is weaker, our rotational failure go below that. So it's not that in all cases it will be identical. Only if the critical failure is within the reinforced soil, then both should be more or less same. So here also you'll find this goes deeper like this. So normally in RISA, we don't worry about individual layers, but normally we, like intuitively always we put the stronger layer at the bottom only like that. But then the process automatically takes care of that. Then in the BS, it has a limit state design with like partial factors and like that, material factors also. But whereas FHWA, like for the walls, they go for a limit state, but slopes, again, normal, like the lumped parameter. This is more convenient because, see, most of the slope stability programs, like we cannot put a, I don't know, both are, it's not a limit state approach actually. I think it's more of a limiting equilibrium only. So it's more convenient. It prescribes the factor safety. Now, what should be the factor safety? Like, if I look at FHWA, like minimum, like a 1.3 earthquake. But many other countries I have seen, like if it is a normal slope, unreinforced, then 1.3 is enough. But if it is a stabilized slope, like a reinforced soil, so then it's okay, let's go for 1.5, like that. And if it is a railway embankment, our RDSO specifications for railway embankments, it is 1.4 minimum, like that. So depending on the particular code applicable, we have to select a factor of safety. Then if we come to the facing, as I mentioned, if the angle is 45 degrees or less, then we don't need a special facing. The reinforcement comes and stops at the face. So these are the primary, like which resist. Then at the, here we have something known as a secondary, like that. So that is, we may have like this primary intersects the major failure planes, stabilizes, but close to the face we have very shallow failure surfaces. To prevent that, we have the secondary. And secondly, to improve the compaction, like in the soil. Otherwise, near the slope face, achieving compaction is not easy. So secondary, basically what happens, once you have the secondary, it gives confinement to the soil actually. So it facilitates compaction. Then we can put a like erosion control mat, like a coir or jute, and have vegetation. Like then sometimes what happens, we need topsoil to get the vegetation like that, because sometimes the imported soil, it may not be good for vegetation growth actually. So some topsoil may have to be put. So again, this is also a important part, erosion control. Otherwise, what happens if you don't protect it again our slope is going to fail in spite of all the reinforcement. Suppose we ignore the erosion control, there also we end up with problems actually. Like we can have a green facing. Then if it is steeper than 45-degree, we have to have a wraparound face. The reinforcement come to the face, goes up and again back into the fill. This will be at least minimum say 1 meter. So it can come down like this, or it can be even straight also. And sometimes something like a tensor geogrid, it is connected with a bodkin like that. That is also possible. But if it is a polyester, we cannot do that. Then again, this wraparound, we cannot construct it just like that. We need some other, like a formwork kind of thing like that. Because soil as such, like we cannot achieve this actually. So one option is to have a temporary formwork, like full height like that. So this frame and maybe some plank or something is cut, then slope is constructed. Then this can be removed. It's just like our shuttering for concrete like that. But then this compaction could be a problem here like that. Then we have something known as clamping formwork. That means each layer we put this temporary. Once you compact this, you just move it up like that. Several arrangements are possible like this. Then very common techniques is use soil fill bags actually. You can stack those bags, then form the wraparound. These bags after a period of time, it will degrade. Fine, no issues. We can also use welded wire mesh like that. This is again temporary like that. See, once the wraparound is formed, vegetation is formed, even if it corrodes and goes, no issues like that. But then we need not galvanize actually. We can use normal welded wire mesh. But if it needs to be permanent in some cases, then it has to be galvanized. This is like a Shillong bypass. This all like a wire mesh. With the vegetation fully established. We can also have like what is known as bioengineering with woody vegetation. Like see, normal turfing is with grass type vegetation. We can also have this woody type plants planted into the fill like that. That is also possible. Then sometimes what happens, vegetation is not possible everywhere. Like if you have a very hot and dry climate, then sustaining vegetation is not, or if the slope is steep, like steeper than 60 degrees, then having vegetation is a challenge. In those cases, we can go for a stone face like that. Again, we have this welded wire mesh. We have the reinforcement wraparound. Then maybe half a meter or something, we put a stone backfill like that. In this case, the welded wire mesh has to be permanent actually, because if that mesh goes, the stone also will not stay. And not only that, because we don't have vegetation to protect against UV. So the wraparound part also will degrade after some time. So we need a permanent. We can have a gabion face, like with the gabion setback, we can have different type of slope angle like that. So again, here probably the connection strength, that also we may have to check like here. Another option is geocell, slightly expensive material, but still very versatile. So here again, so here the inner cells, we can fill with aggregate or sand. So that helps in drainage. Outer cell, outermost, we can fill with topsoil. It can support the vegetation like that. Or if it is even a riverbank protection, like we can fill it with the gravel or even concrete. Like, so it's a very versatile material. Like. Then there are guidelines available, like so different conditions, like different slope angles, different types of fill materials. What are the suggested phase treatment? Sometimes for which vegetation is acceptable, where wraparound is required, this kind of guidelines are available. So we can use that.